Morning, Dr. Jia.
Hello, good morning.
Morning.
Yeah, so did you watch, Mariano, did you watch the recorded lecture last time?
I couldn't find it. Where is it?
Oh, in the Canvas. So there's an announcement. Let me share those with you. Sorry, I thought you know where it is. Let me show you. Okay. Oops. So I usually put the okay, put the link.
Oh,
Yeah, it's here. So the record of this year's lecture. So if you click this one, so everything is here. So this is last time.
I see.
Yeah. So just look at the announcement. So each time I just updated this announcement, the record of this year's lecture. Yeah. All right.
Thank you.
Sure. Okay, let's get started. Right. Okay. Okay, so today we're gonna talk about I think chapter number 8. We have learned how we can construct a linear model, right? Y equals to B0 is the intercept plus B1. Suppose this is the additive effects Z, times Z, and plus W is the indicator for the dominance effects, right? B2. So that's the linear model we can use to test a single locus in the genome. So if we know how to do this, it's easy for us to repeatedly use this method to test each possible locus on the genome. We call this as a genome scan. So by doing genome scanning, there's another very commonly used name, GWAS, Genome-Wide Association Study. You can scan the entire genome and test each genomic locus and find all possible genomic loci that are contributing to the phenotypic variation. All right, so this is what we're going to learn today. Okay, so this is the example, a simple example we're going to use for today, and we're going to see how we're going to use what we have learned to analyze this data and identify the QTL. QTL is the quantitative trait loci, right? So we want to scan the genome to identify the trait associated loci. All right, so this is a very old data set, as you can see. So Dr. Xu actually analyzed this data sets about like 15 years ago. So which means like this data is probably like maybe 2 decades ago. And at that time, we do not have very advanced genotyping technology like today we have, right? So at that time we did not have like whole genome sequencing or a very advanced genotyping array. So what they did in that back to then is to use something like this, the microsatellite markers. All right, and the number of those kind of molecular markers is quite limited. So this is at that time, this was a very good experiment they actually studied, let's say, 110 mice in a F2 population. And for each F2 mouse, they genotyped the genotype for 193 markers. So those markers are all microsatellite markers, not the single SNPs, single nucleotide polymorphism. It's something like the repeats or short repeats, or some very special like pattern of the DNA that can be used for this purpose. So this is the data. Okay, and so if you are interested in how the QTL mapping was used to analyze this data sets, so you can find this paper and Dr. Xu's paper published in 2009. And so you're going to see some results in that paper. So this is what we can get by the genome scanning, right? So for example, we have this many markers, right? For each markers, we can use this model. So I try to link what we have learned before to the new approach. So here we repeatedly use this model to test each of these 193 markers. And on top of this, so because there's only like 100 markers, right? We can also test the genomic region in between. So here, right? The good thing is like, so even we only have this many markers, so we still can do a good job for the QTL mapping. Why is that? Because we knew, right? We knew like even we have a marker here, but if the QTL, the real QTL is very close to this marker, then there's a LD, there's a linkage between this marker and the real QTL. Then, so we can leverage this kind of linkage or LD to help us to do the test and identify the real QTL in the genome. Right, so this is what we can do for the scanning, genome scanning. And okay, so this graph actually shows the Manhattan plot. This is very similar to the Manhattan, a classical Manhattan plot that we can get for a GWAS. So here, this is a log score. So we have talked about what log score means, and this log score actually represent the significance level for each tested loci. So for example, this is a cutoff or threshold. So any signal going beyond this cutoff, we say it's a significant test, which means like, so this signal coming from this locus, so this genomic locus, which means like this genomic locus, the signal is very significant. And we believe by doing this genome scanning, we identify the genes in this region that are likely contributing to the variability of the phenotype of interest. So this is the Manhattan plot. And so besides getting the p-value for the test, we can also estimate the genetic effect, how big this effect will be, right? At each locus. So for example, that's the region showing the significant signal, right? And we can also estimate the magnitude of the genetic effects. So that's the QTL effects. All right, so I just very briefly introduce these two graphs to you. So if you are interested in this, or if you want to use this paper to for your term paper presentation. Yeah, go ahead, and you can spend some time on this paper and see how Dr. Xu was using the method to scan the genome. Okay, now let's look at the details. All right, as I mentioned, in the past, we were very limited to get the genomic information for any individual genome, right? But now we have very advanced technology. We can measure like more than a couple of million SNPs markers along the genome, and this will give us way more like more than sufficient information for us to do the GWAS analysis. But in the past, so people had to deal with like the sparse markers. So for example, in this study, we only have like, in the mouse genome, we only have like less than 200 markers, right? So suppose this is a marker. And suppose this is the real QTL. QTL means like a real gene that is responsible for the traits of interest. And if the marker is very close to this QTL, then there's a good chance for us to identify this marker by doing the genome scanning, because yeah, this marker actually is quite linked. It's very well linked. There's a strong linkage between this marker and the QTL of interest, right? So this is the basis we're going to use to test each possible locus on the genome and test and find out the potential QTLs for the traits. All right. Again, we're going to leverage this model, right? I hope everyone are very familiar with this model. We should be familiar with this, comfortable with this model, right? All right. So suppose this is a F2 population. Yeah, this is a mouse F2 mice population. And can anyone tell me what is this model? What this model is? So we only have like B1. We do not have B2 here. So what does this model mean? So put it in another way. So are we testing both additive and the dominant, or we just test the additive effects here?
Just the additive.
Yes, just additive, right? Because we only have B1, right? If I put like B2 there, XJ X, so that means like we want to test both additive and the dominant. Okay, very good. All right, and so suppose this is the genotype. This is the gene. So the X represent the genotype of this QTL of interest. So we want to identify this QTL. However, the real genotype for this QTL is unknown. So we do not have the information about the genotype for the QTL, right? But fortunately, we have the genotype for this marker, which is nearby. So then we can do some like statistical inference. So what we can do is like, based on the known information, the marker information here, conditional on, so we put a vertical bar here, right? The vertical bar in the statistic means like conditional on the marker information. So we can calculate the probability that X equals to 1, which means at this QTL, the genotype is the first type, A1, right? Or we can also calculate, given the marker, what is the probability that this QTL takes the genotype of 0, which is the heterozygous genotype, and so on. And we are good at this, right? Once for a unknown variable, if we knew all possible outcomes and the associated probability, the probability actually can be calculated based on the recombination frequency, right? The map distance between the marker and the QTL. So that's what we already knew. And then we can easily calculate the expected value for this random variable, right? Although we do not directly observe the genotype of this XJ, which is the genotype for this QTL, but we are able to calculate the expected value for this X genotype, right? Then, okay, we can replace this unknown thing by its expectation, right? The expectation, so I hope you know how to do this, right? So we have 3 values here, and we have the 3 probability associated with these 3 values. Then we can easily calculate the expectation by doing this, right? Pi xi I equals from 1 to 3. So if you calculate this, that will gives you this, right? Because this one is 0, so this one times this will be 0. So you only see this and this. Okay, any questions here? So this is the very fundamental calculation. All right, the key point here is like, because we do not see the genotype for the QTL, right? So we want to calculate the expected value for this by using the marker information. And the marker, we knew the distance between the marker and the QTL, then we can easily calculate the R, the recombination frequency, and this will help us to calculate the probability here. Right. Okay, so now this table actually summarizes how we can calculate the expectation of X, right? So for example, so given the marker information, so suppose the marker takes this genotype, suppose, and given that the QTL still can take 3 possible genotypes, right? Yeah, right. All right, then what is the probability? Suppose the marker takes the genotype, the first genotype, and the QTL also takes the first genotype, which means there's no recombination, right, between them. Then the probability will be 1 minus this and 1 minus this. Does it make sense? Yeah, the same is like this, right? If given the the marker takes the first genotype, but the QTL takes the heterozygous, you see some like recombinations there, right? So this is how we calculate the probability and so on. So we are familiar with this. All right, so this is how we calculate this probability here, right? And once we have this probability, we can easily calculate the expected value for X. So let me show you the next slide. All right. All right. So yeah. So now look at this model. So we have B1 and B2. So here we actually are testing both genetic effects, right? Dominance model. So we test additive effects, and we also at the same time we want to test the dominant effect as well. For each locus, for each potential QTL, right? Okay, now for the additive effects, one, we have like 3 possible genotypes for the QTL. We use this coding, these numbers, quantitative numbers, to represent this variable, right? So we are familiar with this. Okay, for the same genotype, for the same 3 possible genotypes, we use different X2 to code the dominance effect. So when the genotype are 2 homozygous, we put 0 there because there's no dominance effect. Only if the genotype is a heterozygous, we put 1 here. So this is how we code this 2, right? And okay, now we have for the first variable, we have this, and we have the probability associated with that, then we can easily calculate the expected value for this x1, right? The same thing, we can calculate the expected value for the x2, all right? Then, so we just follow the exact exact model or method we used for testing the gene and the phenotype association when all the data is available. So the full model. So we just replace the missing value by its expectation. So this is what we do here. So we have learned this before. Once we can calculate the expected value for x1 and x2. Okay. All right, so this table actually shows the linkage between the marker and the QTL, right? And we knew the marker can take, so if this is a backcross design, let's see. Yeah, this is a backcross design. Okay, in a backcross design, the marker can take two possible genotypes, either 1 or 0, with equal chance. And so we can calculate the variance of the marker, which equals to 1/4. So this is for the backcross design, right? And given this information, so we can calculate the covariance between the marker, and the QTL. So this is how we calculate, right? So we just follow the formula, the covariance, the formula to calculate the covariance between the marker and the QTL. So that's the number. And and we know in statistics how we calculate the correlation coefficient, right? So if we use this formula, we can calculate the correlation coefficient between the marker and the QTL. So this is actually equivalent to the regression coefficient if you want to regress the QTL using the marker, right? Yeah, so this regression coefficient is equivalent to this correlation coefficient. All right, okay. So this is what we can do. And I'm going to show you one thing here. Because the real genetic determinant for the gene is the QTL. Suppose this QTL has an additive effect equals to A. However, because we do not see the genotype for this QTL, right? So what we can do is like we can leverage the information, the genotype information for the marker to estimate this A. If we just use the marker information to estimate this A, so we no longer estimate the real A. So what you can estimate by using the marker genotype information, so it's different from the real additive effects of this QTL. So the estimated effect will be shrinked. So if you just use the known marker information to estimate this A, you're going to get this rather than A. And we know this is less than A, right? So you're going to see a reduction in this estimation. Okay, very good. I'm going to show you why this is this. So suppose, so this slide, we can calculate the covariance or the correlation coefficient between the marker and the QTL, right? Then we can move forward and to see, okay, all right, so this is the model we use, right? We want to use this regression model, so this is a backcross design, okay? And here we just estimate additive effects. So because we do not know the genotype of this QTL, so we just replace this missing value by its expectation given the marker information. So this is how we understand this formula. All right, and this is how we calculate the expected value for this missing genotype, QTL genotype, given the marker information. So we can use this, right? And if we replace this in, if we replace this by this formula, we got this. And okay, so this actually, so we rewrite this linear model using this, and we can group this together to generate a new B0 star, which is the intercept for the regression model, right? And this is the regression coefficient, the B1 star, and the marker information, all right? And we can rewrite the model into this. Now, since from here, as you can see, so if we just use the marker genotype to estimate the genetic effects, so what is the B1 star here? Actually, B1 star equals to this, not B1 itself, right? B1 is the real additive effects. So, but if we, B1 is the real active effects associated with the QTL. Because we do not know the genotype of the QTL, so we use the marker instead to estimate this additive effects. But when we rewrite this model, this is what we can estimate it, right? So the new regression coefficient, which is the B1 star, is not exactly equal to the B1. That is the original additive effects. So there is a reduction factor here, right? So this is this. Okay, so by doing this, I just want to show you. So when we use a marker instead of a QTL to do the estimation, the genetic effects, additive effects estimated by using a marker has been reduced by this factor. All right, does that make sense? Any questions here? And oops. So, all right, let's go back to this slides. Okay, so this is what you can estimate it, right? From the marker. So suppose the marker is very close. Let's see, marker is standing just within or just very close to this gene. So what will be the consequence here? So if this is the case, so the marker is here, the R will be close to 0, right? And this will become A, is equivalent to A, which means if your marker is just standing within the gene or very close to the gene, then using this marker, you can very accurately estimate the additive effects for this QTL, right? So that's why right now, with the advanced genotyping technology, so we can do a very good job much better job than before, right? Because we have a good chance to genotype the marker either within the genes of interest or very close to the gene, and then that marker can give us sufficient information to accurately estimate the real genetic effects for that QTL. Does that make sense? Right. Yeah, okay, very good. So even in the past, still okay, because the recombination is actually a very rare situation, right? So as long as the marker is within some region, genetic region from this QTL, so we can still do the genome scanning. And there's a good chance for us to identify the QTL that are responsible for the traits. All right. So this is the kernel, the core knowledge about the statistical genomics. So so the name is fancy, like it's statistical genomics. Actually, the kernel is very simple. So you just need to know how we use this linear model to test a single locus. Then you just expand this method to scan the genome, and then you can get what you want, right? All right, it's very easy. Okay, very good. Let's see. Okay.
I have a question, Dr. Chia.
Yes, go ahead.
So this test would be able to quantify small effect loci.
To test what? I'm sorry?
Small effect loci?
Yeah, sure. Yeah, that's right. So, okay, that's a good question. So in the past, because we have limited marker information, so usually like 10 years ago, so with the limited genomic data, we can only identify the major loci, which means like the loci that have a major or big genetic effects. But now the reason why is that because the chance to get a marker within or very close to the QTL is small, right? In the past, so if that is the case, so you can always, so even this QTL is a major QTL with a big genetic additive effects. However, due to the limit of the marker information, so you may only estimate part of this genetic effect. So that will affect your statistical power for detecting even the major major QTL, right? For the minor for the QTL with a very small effect, so usually it's very challenging to detect those QTL with the minor effect in the past. But now it's totally different because you have like very dense. So you have like more than a million of the SNP, right? And they are very densely distributed along the genome. So this will significantly increase the chance to detect the small effect QTLs for the trait. Does that make sense?
Yes, thank you.
Sure. Yeah, very good question. So to answer your question, this is the this is the solution. So why? Because the quality. So so how can we so how well can we scan the genome and detect the small effect QTL? Totally depend on this formula, right? Yeah. Okay.
I just had a quick question.
Yes, please.
So you mentioned that this is the framework for QTL, but would it still be the framework for something like GWAS?
Yes. So yeah, that's another. That's also a very good question. So I think many students are confused by this two concepts, right? GWAS. Actually, yeah, these two are very much related to each other. So usually QTL mapping means like we use a specific population, let's say F2 or backcross or some other like real population. Because for this specifically designed population, we try to find oops. Oh, sorry. Let me QTL and GWAS. So actually, we use the same model or very similar model or strategy to analyze both data. The major difference between these two is like, so for QTL, we often refer to a specific population like the F2 backcross, but for GWAS, we often deal with a natural collection. So for example, the citrus collection or a human population to study to identify the genetic determinants for a disease trace or something like that. But the QTL usually is quite often used in a breeding program when we deal with some specific population here. Does that make sense?
That makes sense. Thank you.
And sometimes we just use these names. So we treat these two design interchangeable. So and usually I use GWAS for both of them. So it doesn't matter. But the answer is like, yes, we use the same setting, the linear model like this, to test the association between each genomic locus and the trace variability. Okay. All right, and okay, so one, we successfully estimated these parameters here. So B1 is the additive, right? B2 is the dominant. So, okay, so if we, for any locus, for example here, genome, if we can estimate this two genetic effects, we can, what we want to do is like, we want to test if this estimated genetic effects are significant or not, right? There are two possible ways for us to test this. The one is use the likelihood ratio test. So this is how we calculate the likelihood based on the NAM model. And this is the likelihood calculated from the alternative model. So using the estimated parameter here. So this is a chi-square distributed random variable, and we use log score for calculating the p-value here. And also, there's another way to test this genetic effects. We can use this F test. So this is something we have learned before, right? So I hope to remind you of this. So this is actually, this is a matrix notation. So actually, you can treat this as something like this. The B square divided by the variance of the B estimation, right? And this is actually the signal to the noise ratio. So by doing this, we can test if this genetic effects estimated from the data is significantly different from 0 or not. Or not 0. All right. And both methods can give you the p-value. And in the genome scanning, so you can use, for example, this is the locus that we are testing. And based on the p-value, either from the chi-square distribution or from the F distribution or from the word test, the chi-square distribution, you can plot the signal using the minus log p-value. And this is what we often use in the GWAS, right? Or QTL mapping. This is the y-axis. And if this signal is high like this and passing some threshold here, then this is the genomic region that you are looking for. And because, look at here, so this minus log p is large, say equals to 9. So what does that mean? That means like the p-value actually in this case for this locus here equals to 10 to the minus 9. So this is highly significant, right? All right. Any questions so far? Okay, let me give you a very brief summary here. So far today, we learned how we use the beautiful model we have talked about many times, right? So this is the model. Like Adrian just asked, yeah, this is the kernel setting we often use. Plus x2, v2 for testing a single locus. And then when we are good at this, we can repeatedly use this to scan the genome, and we get lots of test results along the genome, and we can use this result to generate a Manhattan plot like this. So once you know how to do this, you will be able to produce a very good, very nice plot of high quality for the publication, for your own publication in the future. Right. All right. And so in the past, because we have a very sparse markers to help us do this kind of genome scanning, so that's why we have to use something like this. Like for any possible locus without genomic information, we have to calculate the expected genotype for this locus based on the marker information. But now this is not an issue anymore because we have a very good advanced genotyping technology to help us get very good genomic data. All right. Okay. All right, now the next very important topic here is because if you are just testing, if you just test one locus, that's okay. You always use the 0.05 as the cutoff, right? As the threshold to help you either accept the null hypothesis, which means this locus is a neutral one. It is not related to the phenotype, or you can reject the null hypothesis. Means okay, the p-value is less than 0.05, which means like the genetic effect estimated for this locus is non-zero, and we believe this locus is somehow related to the phenotypic variation. Right? Okay, so that's easy for a single test. Okay, now, since we are dealing with the genome scanning, so we are not just test one locus, we test many locus here, right? Many, like maybe many thousands of the locus. Then we cannot. So if we want to guarantee a good control on the type 1 error, I hope you still remember the difference between the type 1 and the type 2 error. So we are trying to control the type 1 error in this kind of multiple comparison or multiple hypothesis testing. If you just test one locus, that's a single comparison or a simple hypothesis testing, right? If we scan the genome, and if we want to make many thousands of the hypothesis testing at the same time, simultaneously, so this is a multiple comparison or multiple testing problem. So for each single test, we cannot use the 0.05 anymore, because I'm going to show you why. If you still use this 0.05 for each of this individual test, you're going to have a very enlarged family-wise or experimental-wise type 1 error. So let me show you why this is. So rather using this 0.05 for each test, we have to use a very stringent cutoff for each locus. For example, in this case, we may use this as a cutoff or threshold for testing each individual genomic locus. I'm going to show you why. All right. Let's look at a single test. So for a single test, we used 0.05 as a cutoff. So suppose this is a neutral locus, and this locus actually is irrelevant to the trait of interest. All right. Okay, and this distribution is centered by 0, right? Okay, what we have learned before is like, so we have a cutoff here, 0.05, right? And this 0.05 actually specify the rejection area here. The shaded area equals to 0.05, right? What does that mean? That means like, even this is a neutral loci. So even this locus is not related to the trait of interest. However, there's still a small chance, 0.05, that you can estimate a non-zero, non-trivial genetic estimate, genetic effect from this locus. Does that make sense? So that's the type 1 error. Type 1 error. Or put this in another way, is like, even this is a non-hypothesis. Even the non-hypothesis is true. So if we use the 0.05 as the cutoffs, the probability that you make a correct core, or you're going to accept a non-hypothesis, equals to 0.95, right? This is the correct probability. And the mistake probability, or type 1 error, is even the non-hypothesis is true. Even this is a neutral locus, you still have this probability to make a incorrect core, to reject non-hypothesis. All right. So I hope this is clear. So this is the probability of correct, and this is the probability of error. Right. Now, this is for a single test, right? Consider if we want to test the two loci, and each of these two loci, both loci are neutral. All right. If we want to consider, test these two loci simultaneously, this is a multiple comparison problem. This is a multiple testing problem. All right. Okay, let me ask you, if we want to test these two loci simultaneously, what is the probability that you make two correct cores for both loci? What is the probability? Since these two tests are independent, so we can simply multiply these two probability, right? Do you agree? So this is the probability for you to make two correct core, right? Does that make sense? And this actually equals to this times. Does that make sense? And if I ask you, okay, so if this is the probability that you make two correct core for testing these two loci, so what is the probability that you will make at least one miscore for testing these two loci? What is the probability? You're going to use 1 minus this, right? Because this is the corrective course for both. If you use 1 minus this, this will be the probability for at least one error. So I put a bar here. So this probability actually includes like you make one mistake, or you make another one mistake, or you make both mistakes, right? So that's how we calculate this probability. So this is like this, all right? So think about, rather than testing two loci simultaneously, if we test 5 loci simultaneously, so then we can easily understand this calculation. So if we want to test 5 loci simultaneously, what is this probability? This is the probability that none of these 5 tests are mistakes, are errors, right? And if we use 1 minus this will be the new type 1 error, family-wise type 1 error. Okay, very good. All right. How do you think about this? What do you think about this? Is this acceptable? So if you test 5 loci, and if you still use 0.05 for each individual test, this gives you the family-wise or experiment-wise type 1 error. Do you accept this error rate? No, this is too large, which means like it's too easy for you. If you still use 0.05 as a cutoff for each of these 5 tests, you're gonna have this big family-wise type 1 error, which means like it's very easy for you to make a mistaken call, right? Error call. So we don't want this happen. So when we deal with the genome scanning, where we test many like loci simultaneously, we have to use a very stringent cutoff for each test to guarantee we're gonna get a small family-wise type 1 error. All right, so this is why actually in statistics, there's a big branch to study the multiple comparison. Lots of scientists, statisticians are spending a lot of time and efforts to find the best way to control this family-wise type 1 error when we deal with multiple comparison or multiple testing. I hope this is clear. Right.
Sorry, I was following along pretty well to the very last part. So I understand that the probability is really big, but should the take home be for this family-wise comparison that you actually don't want to compare 5 sites because it's just too big?
Sorry, I didn't follow you. So you mean the 5 is large?
Yeah. So I got everything up until like the very last part where you.
Okay.
So I got lost until right after you said that this probability is very large. So what's the take-home message for it being too large?
Yes. So this error is too large, but this is this doesn't mean like the 5 is a large. 5 actually the number of the tests in a multiple comparison. Actually, 5. I consider 5 is a small number. So I just use this to because this is easy to understand this formula. Okay, now think about the genome scanning. So you are testing probably like 3 million markers together simultaneously. That's a big number, right? Which means like instead of testing like 5 loci simultaneously, you're gonna test like 3 million loci simultaneously. That's a big thing. All right, if that is the case, so let's see what happens here, right? So when we test 1 locus, that's fine. So we can use the 0.05. That's very safe. Now, if we use 5, then when you still use 0.05 for each of these 5 tests, this will give you this family-wise type 1 error, right? This is too large. Which means if you use the 0.05 for testing this 5 loci, so you have this probability 0.2 probability to make mistaken course or the incorrect course. All right, let's think about this. So this is a large number of the comparison, right? So if we test 3 million, and this number will become 3 million. So I don't have the calculator, so you can help me to calculate this. So if this 5 becomes 3 million, and this number will be very close to 0, and this family-wise probability is close to 1, which means you can never make a correct call. You always make a incorrect call. So it is too easily for you to to reject the non-hypothesis from the 3 million, and which means if you use this cutoff 0.05 for each of this, you will identify a lot of false positive signals. It's very likely for you to claim the entire genome is associated with the phenotype of interest.
So how would you decide what the cutoff is, or do we just use a different test for large?
Yes, I'm going to talk about this shortly. Yes, here I just show you if we do not change this cutoff for individual test, we're going to have problem here, right? So there are a lot of things available for us to get a good control for the family-wise type 1 error. So one thing, I hope some of you have already heard about this, right? Bufferoni correction. Have you heard of this before?
No.
Okay, all right, good. All right, so this is one way that can help us to control the potential enlarged, inflated, family-wise type 1 error. All right, okay. So suppose this is the nominal type 1 error for one test, let's say 0.05. However, if in your experiment, you want to test this many loci, K, so K is a large number. Okay, now, so how shall we set up a alpha for the single test such that the beta here, actually, this is not the type 2 error. So we use beta here as the experiment-wise type 1 error or family-wise type 1 error. Okay, so how can we, to what extent, if we reduce this alpha, can we achieve beta equals to 0.05? So here we want to achieve that the family-wise type 1 error equals to 0.05. So how can we find the proper cutoff for alpha for each single test? So this is the one way the Bufferoni correction is saying here. We divide this target 0.05. This is this, right? By the number of the test. So suppose here we test 100 loci, and if we want to achieve the family-wise type 1 error still equals to 0.05, for each individual test, we have to use this stringent cutoff for single test. Does that make sense? So for 1, 2, 3, and so on, for 100 tests, we have to use alpha equals to this small thing to achieve a family-wise or experiment-wise type 1 error is less than 0.05. Any questions here?
Are there any drawbacks to this correction?
Are there any what? I'm sorry?
Drawbacks? Or
Yes, yes, of course, of course.
Okay.
Yeah, this is the first one, but people don't like this because this cutoff, this correction is somehow very stringent, too stringent. So sometimes if you use this correction, so you'll get nothing. You get nothing when you scan the genome. So that's why people proposed another alternative. So this is a better one called the SIDAC correction. All right. All right. Let me write this. So this one gives you a little bit more relaxed cutoff, because yeah, sometimes this is the problem. So in the future, when you do the genome scanning, or if you want to do the differential expression analysis, in both cases, you have to consider using the correction, right? Because you want to control the inflated type 1 error. However, if you choose to use the Buffronic correction, sometimes you cannot identify any single differentially expressed genes or any single locus that is responsible for the traits. So then, if this is the case, either you have to go back to check your experiment steps to see if there's some problem there, or you can try some relaxed cutoff correction. For example, this is the one you can consider, all right? And this is how we calculate the family-wise type 1 error, right? And so by doing this, if you if you rewrite this formula and get the solution for alpha, so this will give you a relaxed cutoff for each individual test. And so when the beta is small, which means if the type 1, the family-wise type 1 error is small, so these two correction actually identical, which means like if the type 1, the family type 1 error is like 10 to the minus 5, then these two corrections are identical. But usually we do not use this too stringent family-wise type 1 error, right? We use beta equals to 0.05. So if you use this, you can calculate your alpha. This is a very soft, relaxed correction for multiple comparison, right? Any questions? And yeah, Mariano, let me tell you, let me give you another even more relaxed the cutoff here, the permutation. So this is sometimes this is we call this ad hoc method. So if any of those stringent cutoff correction cannot give you satisfactory results, so you can always use the permutation, empirical permutation based on your data. Yeah, so this is, let me see, what time is it now? All right, we have time. So before I talk about this method, the permutation test for controlling the family-wise type 1 error. So any questions for the previous two method or the previous model for scanning the genome? Any questions? Okay. Permutation test. So we did something like this, the bootstrap, right? Do you still remember? So when we talk about the mapping, so we try to put the different genes, link the genes on the genome, on the chromosome in the right order. So in that place, we talk about the bootstrap. Bootstrap is something like the permutation. So here, let me give you an example here. So for example, this is a small sample example. So here we have only 10 plants. Okay, we have 10 plants. And for each one, we can measure some traits here. So this is the traits. And we can see the variability of the traits, right? And for each of this plant, we have 5 markers. So that's quite limited, right? We only have 5 markers. So this is 1, 2, 3, 4, and 5. All right, we want to test if any of these markers are associated with the trait. All right, so this, let's say this is a F2 population. So the H means the heterozygous. So for marker 1, all 10 individuals have the genotype of the heterozygous number 2, right? 0. Okay. And for the marker 2, you're going to see some are heterozygous, some are the first genotype homozygous, and the other one is the second homozygous genotype. So U means like unknown, so missing data, missing genotype data here. So what we can do is like, can anyone tell me, so how can we use this data? So if you have this data, if in the final exam I gave you this data, so what can you do with this data to test if any of these markers is associated with the trait? Can anyone tell me?
You would randomize it.
Yeah, that's the last step, right? So when you have your estimation of the genetic effects, let's say the additive effects for mark 1, then you can calculate the p-value using the permutation. Yeah, that's the last step. So first, before that, before we do the permutation, what can you do to test whether this marker is associated with this phenotype? So we can use the model, right? So yeah, my question, I hope yeah, so everybody can know this. So if we want to analyze this data, we can use this model. Let's assume we just want to test the additive effects. Okay, now we already have the Y variables here. How about the X? So for example, if we want to test if marker 2 is associated with this phenotype, so we need to get X variable, right? X variable for the first one, it is the heterozygous, so that's 0, 0, 0, 0, 0, 0. How about this one? A.
That'd be 1.
Yes. How about B? Minus
0.5.
1. Yeah.
Oh, minus 1.
Yeah, the 0 and 0, right? So this is a simple example here. So if you have this information, so you know how to get the BX1 here, right? B1 is the additive effect we want to estimate. So we don't know here. If I want to estimate the B2, which is the additive, the dominant effect, and this is associated with the X2. So how about X2 here for this individual? Heterozygous. X2 must be 1, right? 1, 1, 1, 1, 1, 0, 0, 1, 1. Any questions here? So this is very, very important. Yeah. If I give you something like this, you have to figure out the code for these two variables here. Any questions? Okay. So if you have this, right, you can easily calculate. You can use the code. I can. So in the final exam, so I will give you an open book. So you can refer to your lecture notes, your own notes. You can use my R code. You can reuse those. So, but you need to know which code you need to use, right? So once you can successfully code these two variables, random variables here, then you can use the code to estimate this, this, and this, and do the test, right? And okay, so suppose for this marker, you successfully estimated the B1 is additive, right? And you can also estimate the variance of the B1, right? Then you can construct this is a word test chi-square. This can help you calculate the p-value for this locus. Does that make sense? So this is what we can do now, right? This is one way to calculate the p-value. And once you calculate this p-value, you have to do the correction, right? Here, because we test how many markers here, we test 5. So instead of using the 0.05, if we use the Bufferoni correction, so you have to use this cutoff to make your call, right? Does that make sense? Okay, so this is one way that we deal with this multiple comparison. The next way, the new method that we can use is to do the correction through this permutation. All right, now, Adrian, let me know. So what is the next step? So if we want to use the permutation to calculate the p-value.
Then we want to randomize values.
Yes. So this is something that you would like to present in your term paper, right? Yes, very good. Yeah, that's a good paper. Yeah, thank you. So yeah, so right now I think it's time for you to look for a paper, a good paper, that covers some of the topic that we have learned in this class, and in the final, so our class grade will consists of 2 parts. Sorry. The 50% of your grade will come from the final exam, which is an open book. And then another 50% will come from your presentation. For this presentation, so you need to find some paper, find a paper that covers some of the topics we have learned. You will have like each student has 10 minutes. So you can use like maybe 1 or 2, the first 2 minutes to describe this paper, the big picture, like what is this paper about? Like what the main question being addressed in this paper, and what's the method they use to achieve this goal. So that's the first 2 minutes, and the remaining 8 minutes, so you just focus on one point. The statistical part that you want to for the remaining 8 minutes, you just focus on the topic that you want to you want to discuss. For example, like Adrian, he's gonna talk about the permutation, the bootstrap strategy that paper has used for claim the significant loci, QTL loci, right? So, all right, and after that, so we're gonna have maybe 1 minute or 2 minutes like a question and answer session. Yeah, that's all for your presentation. Okay, so you can start looking for a paper now, and if you are not sure about if that paper is a good one, just send it to me so I can read it and give you my opinion. All right. So permutation. So here, okay, for example, if we want to test this marker, if this marker is associated with the phenotype, so we can get a test statistic, right? So suppose we can get a word test statistic based on the original data. Okay, this is the B1 square variance of B1. Let's say this is the test statistic generated from the original data. Okay, we're gonna do permutation now. So we're gonna permutate this phenotypic value for the first time. So if you randomly randomize this number, so the first number may become here, or just randomize this. All right, and the randomization of this actually is try to disrupt the potential association between the phenotype and the marker, right? If there's a association between this marker and the phenotype initially, by doing this randomization, you're going to totally disrupt this association. Do you agree? All right. Okay, now this is the original test statistic. If you randomize this to disrupt the association between this phenotype and the marker, now with the randomized data, if you redo the test, you're going to get a new test statistic based on this randomized data, right? Okay, so suppose with the original data, you get a very large chi-square statistic, let's say 50. And this actually leads to a small p-value, let's say 10 to the minus 8. Now, if you have a randomized data, so what do you think? The test statistic will be calculated for this randomized permuted new data. Do you think this value will be large or small?
Larger.
No. Okay, because chi-square distribution is like this, right? Something like this. Okay. All right. If there's association between this marker and the traits, you're gonna get a chi-square something like here, 50, which means there's an association between this marker and the traits, right? If you randomize this phenotypic value to disrupt the link between this marker and the traits, then when you redo the test, you're gonna get a very small chi-square statistic, which is close to maybe 1 or 2 here. So this will give you, let's say 2, very small, right? Now we complete the first permutation. Let's do this again. So the second time, what do you think? Something like here, right? So either 3 or 1 or something like this. If you permute this data for many times, so actually this kind of the distribution of the test statistic based on the permutated sample will give you a non-distribution. Do you agree? Non-distribution means like something like normal distribution. So the normal distribution actually is based on what you observed here. So the permutated data, and this will be close to, let's say 2. Do you agree? Yeah, think about this. So if you permute your data many times, you're going to get a bunch of 2, 3, 1, right? Not 50, because 50 is like the original statistic. So if you plot, let's say you permutate your data for 100 times. So what's the distribution of this test statistics based on your permutated data? Do you think the distribution of these numbers will be normal distribution, something like is centered by 2 or 3, right? And okay, now if this is the distribution, this distribution actually is a non-distribution, which means like the distribution of this test statistic is based on the non-association between this locus and the trace, right? And if there's no association, you should get a distribution of the test statistic, something like this. But your original test statistic is something like here. And this will give you an empirical p-value based on the permutation. Is that clear?
So as you keep on permuting, it sort of straddles a mean as, I guess, the program learns?
Yes, the program learns, yes. So the key point is like, what is the purpose of the randomization here? So the randomization process actually try to disrupt the potential association between the phenotype and the marker if there is an association initially, right? by permutating this, you can totally destroy the link between the marker and the traits. So what you can achieve by this randomization is like you can generate a non-distribution of the test statistic if there's indeed no association between this marker and the trait, right? Okay, all right. And once you have this non-distribution, you can easily compare your initial test statistic and to see where your initial test statistic stands within this non-distribution. Because this is the test statistic based on the data before the randomization, right? So if this non-distribution gives you some idea about the test statistic, so this distribution, non-distribution actually shows you what the statistic will look like if there's no association between the marker and the phenotype, right? So you should get something within this, but without the randomization, if you got your test statistic which stands which outstand this distribution, this will gives you an empirical p-value for your test. Does that make sense? Okay. So
Yeah,
I'm gonna
makes
stop
more
here.
sense, thank you.
Yeah, sure. So it's tricky. It's tricky. So I hope like Adrian will re-talk about this topic during our group presentation, and probably he will give you another example to show how the permutation or the bootstrapping can help us to generate like an empirical p-value for the test. And this is a good strategy for control your family-wise, experimental-wise type 1 error. Yeah. All right, I'm gonna stop here for today. And, any questions for today's stuff? Okay, thank you. Thank you, Adrian. All right. Okay, so I'm gonna prepare. So I have already put some like practice assignment on Canvas. If you cannot find them, let me know. So I'm gonna show you where you can get them. And I'm gonna during the weekend, I'm gonna prepare some other like code for you to practice. And you will find some of this code are very useful when you work on your final exam project. So for the final exam, I'm gonna give you each of you a different set of data. So like F2 design, and I knew the answer. So I'm gonna simulate that data for each of you, and you need to figure out which R code need to be used to make those tests, and based on your test results, give me the answer conclusion, and then you can earn your credit from doing that. All right.
Good.
All right. Thank you, everyone. See you next time.
Thank you.
Thank you. Bye-bye.
Sorry, did you say, sorry, did you have a meeting after this? I don't want to interrupt. I can just email you afterwards.
Yeah, I don't have, yes, I can talk to you. So yeah, if you want to talk to me, yeah, we can talk it. Talk about this.
Just no, I just want clarification. Did you say what we have to do to get credit? You said something just now. It sort of like passed over me.
Oh, you mean just now, right? Just now
Something
I said that.
for like the like you said you're gonna put something up and we get credit for it or something.
Oh, the credit. I mean the final exam. The final exam.
Oh, sorry.
Yeah,
I thought we had like homework all of a sudden or something like that. I was like, wait, what? Yeah,
no.
okay.
So the homework is optional, but I think it would be helpful for you to understand the teaching material, and in the final, so I'm going to give you an open book test, and you're going to see some questions there. So you will have some like short answer questions. So you need to provide the answer to my question. And for each of you, I'm gonna simulate some like genomic data and the phenotypic data for a F2 population. Once you have the data, you need to reuse some of my code to estimate the genetic effects for some markers, and you need to test whether those markers are significantly associated with the trait of interest. So you just follow those code and get the answer and write the conclusion. Then I will grade your results and give you the credit, I mean, for the final exam.
Okay, thank you.
Sure. All right. Thank you.
Thank you.
Bye-bye.